Welcome. In this video I'm going to show you how you can perform a power divergence test using Python. I'm using Jupyter Lab with a Python 3 kernel. In this video I'm going to be using some third-party libraries to do this, and it will focus on how to perform the test, not if you should perform the test and all the ins and outs about the test. The test itself is probably created by cressie-read. They figured out that this last one is a generic formula for quite a few other tests, which uses a lambda as a specific input parameter, and then you can, by setting that lambda, you get actually quite a few different tests. Because it's using a chi-square distribution, there are often some conditions based on the expected counts. So for a goodness of fit test, it's often said that it should be at least 5, and for a test of independence, at least 1, and no more than 20% of the cells should have an expected count less than 5. Also, because it's approximating a discrete distribution, you could apply some kind of continuity correction, either from Yates, which is actually only 2 by 2 tables, Pearson, or Williams. To show you how this can be done with Python, I'll first load some example data. I'm going to be using pandas for that as PD. Then read the file, a general social survey from 2012. I adjusted a little bit. This is all the data in there, but we only need one field for a goodness of fit test. So let's use the marital status, and let's have a look at what that looks like with using the value count. This gives us, for example, 972 people indicated to be married. Then for a test of independence, you actually need two fields, so let's add the gender into the mix. And then we can use a cross-tab function to see a nice cross table. So for example, 456 people chose married and male. Now, to actually perform the test, there are a few different ways that you can go about this. I made my own function. You can download the Python script for that on my GitHub. And after you've downloaded the file, you can actually import the function by using the from and then import. This function just takes variables as input. The second one is of course optional, depending on if you want the goodness of it or the test of independence. You can even set the expected counts if you have some preferred settings for that. Of course the lambda and which correction you want to be applied. Then you can simply feed the field, and it returns for you the test statistic, the degrees of freedom, the p-value, the minimum expected count, the percentage of cells that was below an expected count of 5, and a small description of the test used. You can do the same for the test of independence, and you get the same output. Now, if you don't want to use my function, SciFi is a famous or known library that also has a power divergence function. It uses the observed values, so let's load it in. SciFi stats, import power divergence, and then we can actually simply use that with our frequencies and set the lambda. It will then show the statistic and the p-value. The problem there is that we also usually need to report the degrees of freedom. It's not too complicated. You can simply get that by determining how many categories there were and then subtract 1. So in this case there were 5 categories, so the degrees of freedom equals 4. If you want to do it as a test of independence, it can actually be done with the power divergence function as well. You then have to make use of the dd-off function. In the next library I'll be using that trick, so the same trick there can be applied also for the power divergence function, but SciFi actually has a chi2 contingency function, so if we also load that one in, then we can simply use that and feed it our cross table. I'll use lambda as cressie-read, and again we get the same results. As mentioned before, the stats models, they actually also have a function that can do something similar. So let's load that in. This one needs the expected counts. Now for a test of goodness of fit, it's usually simply the total sample size divided by the number of categories and then multiplied by that number of categories. I can actually substitute this with k as well. And that means that we expect each category to be the same in the population. Now the function then works very similar as before. We just feed it the frequency table, the expected counts and the lambda, and we get the same results as before. For a test of independence, it's a little bit trickier. What we need to do is we need to put all our values from the cross table into one long list. We can simply let Python do that. So I take the number of rows and the number of columns and then create the list. And the list is going to be filled by simply filling out all the values. So I'm iterating here over all the columns and then just store each value and add that to the list. Then the expected counts for a test of independence is usually the number of the row total multiplied with the column total divided by the grand total. So I can calculate those with the sum of the cross table, and if you put axis equals 1, it will do it row wise, the n, and this simply iterates over all of the cells in the cross table and nicely gives us those expected counts. Also, this needs to be one long list, so the same trick as before, but now on the expected counts. And finally, we need to adjust the degrees of freedom, which for a test of independence is the number of rows minus 1 times the number of columns minus 1. The function actually is made for the goodness of fit test and therefore uses k minus 1 minus dd offset. And this is by default 0. So if we adjust that, we can simply say, well, this needs to be our degrees of freedom. And this is the formula it's using. The k is of course now, because we added all the values of the cross table, the number of rows times the number of columns. And then we can simply move this one to the other side and move all of this by subtracting it on both sides to the right hand side. And that should give us finally everything that we need. Unfortunately though, by calculating those expected counts ourselves, we have another issue, is that the sum, as you can see here actually, is not exactly the same due to rounding errors. So what I've done here is, instead of feeding it the expected counts list, I'm actually rounding it to, let's say, 10 decimals. And then hopefully it will actually be the same sum as the observed counts. And that finally gives us the same result as before. Last but not least, there's the Pingolian package, which has a chi-square independence. Again, this one is only for the test of independence, therefore. But okay, it can be used. It has as an advantage that it will actually print out all of them. So I simply feed it the data frame, the two columns that I want. I don't want to have any corrections. And when I run this, I get nicely a few different ones. I can't actually specify the lambda, so it's in here, or I don't think you can actually specify it. Yeah, it does not allow it. You can check out the link there if you really want to. Last thing to check are of course those conditions. You can do that by simply iterating over the list of the expected counts, and if it's less than 5, so it tells you how many there were, and in my case for both the goodness of fit and the test of independence there were none. In another video I'll go over all the formulas. If you're also interested in this Jupyter notebook, I also explain the corrections, so how those were actually done, and hope this video was helpful. Thank you for watching.